2, and till now we have covered elastic plastic deformation, mechanism of elastic plastic deformation. Okay, just let me fast forward. Okay. Yes. So today we are going to start the new topic in module 2, that is the yield criteria. Okay, so most of the topics, as I have come to know through your previous class, that some of these topics, or maybe some component is coinciding with your previous courses, so you might have studied these topics. Okay, so it might be a kind of revision, and those who do not remember, it will be new things for them. Okay, so yield criteria in metals, basically what is the yield criteria, and what does it mean? Okay, so in today's presenter, actually I have typeset it in a very hurry in the morning. I woke up and I couldn't set pauses. Okay, so in today's PPT, it is continuous PPT without any pauses. Okay, so in yield criteria of metals, we already know that the material yields when it exhibits an irreversible staining. Okay, so what does it mean? The irreversible staining, it means that when we try to stain any metal metal workpiece. Okay, so when it exceeds its elastic limit, okay, then some kind of permanent deformation or permanent stain occurs. Okay, so when it exceeds its irreversible staining, which is sustained once a certain level of state distribution is reached. Okay, so we can say the yield stress is the value at which, because we have concluded in the previous discussion that after a point of stress, or after a value of stress, there are two kind of stresses, that is elastic stress, elastic strain, as well as plastic strain, because there is some kind of recoverable part which is called elastic strain part or elastic deformation, and there is some deformation which is unrecoverable. Okay, so the yield criteria, you can say it is an indicator of the stress, and which is the combination of stress component, which includes elastic part as well as plastic part. Okay, so when we are taking when we are considering only one dimensional yielding, you can say in the uniaxial direction. Okay, the stress in any in the uniaxial direction should reach the value of yield stress. Or suppose we are giving this yield stress value y in the case of your tensile test, then your yield stress, okay, or the yield criteria will be sigma equal to y. Okay, where y is denoting your yield stress at of your material. Okay, so in unidirectional component or unidirectional test specimen, we can easily conclude, or we can easily identify or compute the value of your yield stress by conducting a simple tensile test. Okay, so but what about the multi-directional deformation when its material body or a workpiece is subjected to forces from multiple directions? Okay, suppose take one example. Yes. Okay, so in tensile test, we were having a specimen like this, and we are applying load. Okay, so this kind of specimen we consider as a unidirectional force is applied, and your in tensile test, this kind of arrangement is done. Okay, so since the force is one direction, and you can easily compute your yield stress from the tensile test, after which your permanent deformation or there is some plastic strain in your test specimen. Okay, so you can easily compute, you can easily calculate the estimate the value of your yield stress using your tensile test when there is a unidirectional loading. But what will happen? Suppose you are having a component like this. Okay, let me take one. Okay, let us not choose this kind of shape. Let us choose some arbitrary shape. Okay, so suppose this kind of shape you are having, and you are applying certain force F1 from this direction. Okay, F2 from this direction. Okay, and F3 from this direction. Okay, what will happen in this case? How we will determine that material is getting deformed, permanently, or whether the stress is developed in this particular, component has reached the yield stress value. So how we will determine this cannot be estimated by simply tensile test or any other method. Okay, so how we will estimate the state of stress in the case of multi-axial loading. Okay, so this in the case of multi-axial loading, the answer the may be given using the theories which defines your yield criteria. Okay, so yield criteria is you can say it is the combination of stress components in the combination of stress components which include elastic as well as plastic deformation. Okay, and it should have increase your some value, some critical value beyond which your plastic deformation occur. Okay, then only you will be able to consider your plastic deformation. Okay, so in general, when we take a metal workpiece or metal component or test specimen, the most general form of yield criteria may be sigma x, sigma y. That is the yield criteria is expressed as a function of sigma x, sigma y, sigma z, tau x, y, tau y, z, tau zx. Okay, so I think all of you are aware about these terms, what is sigma x, sigma y, sigma z, because you might have read these terms repeatedly in either in material science or manufacturing courses. Okay, so this function, that is function of sigma x, y, z, tau x, y, y, z, zx is equal to constant. So C is representing your yield stress. Okay, and this yield stress value, it is constant for any given material, but it is a function of stresses developed in x, y, z, and whether they are tensile, compressive, or shear stresses. Okay, so in other term, if you want to write in terms of principal stresses, you can write it as function of sigma 1, sigma 2, and sigma 3 is equal to constant. Okay, for most ductile material which are isotropic, the following assumptions are invoked since they have been observed in many instances. Okay, so experimental observations. Okay, so there is no Washington effect. Thus, the yield strength in the tension and compression are equivalent. This is the first assumption, then constancy of volume prevailed, so that the plastic equivalent of Poisson ratio is 0.5. The magnitude of mean normal stress, that is sigma m, does not influence your yield stress or yielding of your metals. Okay, so we will be discussing or we will be detailing using your yield criteria. Okay, so the yield criteria may be, you know, in terms of principal principal stresses, it was given as a function of sigma 1, sigma 2, and sigma 3. Okay, so this function may be further elaborated as function of sigma 1 minus sigma 2, sigma 2 minus sigma 3, sigma 1 minus sigma 3 equal to constant. So this is equal to your yield stress. So we can now define a yield criteria. What is a yield criteria? Yield criteria is a hypothesis defining the limit of elasticity in a material, and the one set on this one set of plastic deformation under any possible combination of stresses. Okay, so ultimately what we are trying to say, that the total stresses in combination of all direction, whether these are the shear stresses or direct stresses, the combination of all these stresses in that is the direct stresses and shear stresses must exceed to a certain critical value. Okay, then only the plastic deformation will occur in the shapes like this. Okay, in the case of uniaxial loading, we were quite sure that when the value exceeds to a value, that is y, in the case of uniaxial loading, your yielding will occur. That is, there will be some kind of plastic deformation, or there will be some portion of plastic strain in the total strain of your test specimen or the metal which is under deformation. Okay, so in order to determining, there are various theories, and there are basically major two types of yield criteria, which are, you know, based on two major criteria. That is, one is maximum shear stress, and another is shear strain energy criteria. Okay, so the first one is called Tresca criteria, and the second one is called von Mises yield criteria. Okay, just a second. Oh yes, so the first one is Tresca yield criteria, and second one is your von Mises yield criteria. So let us take okay, Tresca yield criteria, right? So in Tresca yield criteria, we considered, because it is based on maximum shear stress criteria. Okay, so in Tresca yield criteria, what we assume, or what has been given in the literature, that the difference of the maximum shear stress as well as minimum shear stress must exceed to a given certain critical value. Okay, so suppose this critical value is C, as we are taking it as a constant value, because this will be constant for any particular material. Okay, so suppose sigma max is your largest shearing stress, maximum shear stress, and sigma minimum is your minimum stress. Okay, so the difference of sigma max and sigma minimum should be equal to your yield stress, or you can write in other terms sigma 1 minus sigma 3 equal to constant. Okay, where C is your constant, we are aware C is your constant. I'm a little bit moving, in a fast mode. If there is any query in between, you can ask. Okay, any student, if you feel that you are not able to understand, you can interrupt me in between. Okay, so sigma 1 minus sigma equal to constant. We are aware, and for yes, okay. So for principal stresses, what we consider, that's how we will give nomenclature to these stresses. So sigma 1 is the highest stress, then sigma 2 is less than sigma 1, and but again sigma 2 is greater than your sigma 3. That is why we have taken sigma max minus sigma minimum is equal to C. So that is why which will be the maximum, sigma 1 will be the maximum, and sigma 3 will be the sigma 1 is maximum and sigma 3 is minimum. This rule is taken into consideration while putting the values in the Tresca yield criteria. Okay. So suppose you may be at a situation or in the examination, it may be given that sigma 1 equal to suppose 35 megapascal. Okay. So sigma 2 equal to 45 megapascal. Okay. And sigma 3 equal to 42 megapascal. Okay. So suppose something like this is given, okay, in your question paper, then you have to solve the problem using your Tresca yield criteria. So you will not simply apply this equation sigma 1 minus sigma 3 equal to C. You have to see which is having the maximum value and which is having the minimum value. So suppose in the case in this case, which one is having a maximum value? Sigma 2 is having the maximum value. So what will be the yield criteria for this case? Sigma max minus sigma minimum. Which one is having minimum value? Sigma 1 is having minimum value. So is equal to C. Okay. So this is how we have to be very careful while applying your Tresca yield criteria. Okay. You need not to simply remember sigma 1 minus sigma 3 equal to C. You have to be very careful which rule is valid while giving nomenclature sigma 1, sigma 2, and sigma 3. Okay. So sigma max is equal minus sigma minima is equal to constant. Okay. So let's just try to see in the case of uniaxial loading what happens in the case of uniaxial loading. Okay. So let me move to create new slide. Okay. Yes. So in the case of uniaxial loading, you have say this is your force F. So in uniaxial loading, suppose in the direction you are having stress sigma. Okay, just a second. Okay, so you are having force F, and in this particular unit axial direction, you are having stress sigma 1. Okay. What will be the other stresses? Other stresses sigma 2 equal to we are assuming there is no stress in along any other direction. So sigma 2 and sigma 3 is equal to 0. So in the case of uniaxial loading, how your yielding will occur? Yielding will occur only when your sigma 1 has reached to a yield stress value. Okay. So in the case of uniaxial loading, sigma max is equal to sigma 1, sigma 2 equal to 0, sigma 3 equal to 0. It means your sigma minimum is equal to 0. This condition will be applicable in the case of uniaxial loading. And this will yield your yield strength sigma 1 equal to y. Okay, put these values in this sigma max minus sigma minimum is equal to C. So this will be sigma 1 minus sigma 3 equal to y. Okay, so we can conclude in the case of uniaxial loading, your yield strength will be equal to y. Your yielding will occur when the load or the stresses developed has exceeded to the yield strength value in the direction of loading. Okay. Consider the case of another case, that is the case of your pure shear stress. In the case of pure shear stress, sigma max will be equal to sigma 1, sigma minimum is equal to sigma 3, that will be negative of sigma 1. Okay, we are considering case of shear stress. Okay, then sigma 2 will be equal to 0. Okay, because for shear, pure shear, in the case of pure shear, your two stresses, the forces will be opposite and opposite to each other on nature, and they will be acting on a plane. So on one plane, the stress will be sigma 1, and on another plane, stress will be minus sigma 1. Okay, so using this same Tresca yield criteria, we can conclude that the how the yielding will occur: sigma max minus sigma minimum is equal to C. So try to see sigma max, how much value sigma, it is sigma 1 minus sigma 3 minus sigma minimum or sigma 3. So this will become minus minus plus. So this will become twice of sigma 1. Okay. So we can write it as 2K, which is again equal to your yield strength value. Okay. So using your yield Tresca yield criteria, we can write sigma 1 minus sigma 3 is equal to y is equal to 2K. Okay. Okay. So this is all about your Tresca yield criteria. Now let us take one simple example. I will discuss maybe two or three examples. Okay. So yes. So let us take this example, equibiaxial tension. Okay, so here you can see I have taken this PPT from internet. Okay, so in biaxial tension, you are having loading in suppose this is your x, this is your x, and this is your y. Or you can say it is written 1, 2, 3. X is 1, 2, 3. So in axis 1, we are having stress sigma. In axis 2, in the direction that is y, we are having stress again, because this is the case of equibiaxial tension. We are equally applying equal forces in two directions, that is 1 and 2. Okay, or x or y, whatever you are convenient. Okay, so in this case, your maximum stress will be sigma max equal to sigma 1. This will be equal to sigma. Again, sigma 2 will be, because these two stresses are same, so this will be sigma 1. Sigma minimum, what will be the value of sigma minimum? This will be equal to sigma 3. It will be equal to 0. So now compute sigma max minus sigma minimum. Okay, apply Tresca yield criteria. This will be sigma 1 minus sigma 3 equal to y. Okay. So what is the value of sigma 1? This is sigma. Sigma 3 is equal to 0. It would become y. Okay. So, or you can write it equal to 2K from the previous conclusion. Okay, it is in here. Okay. So this will yield that your sigma yielding in biaxial, equibiaxial tension will occur when your applied stresses has exceeded your yield stress, and this particular value y. Okay. Take another example. We will try to understand what is the effect of hydrostatic pressure in the case of in on the yield criteria on the yielding of your metals. Okay, so in the case of hydrostatic pressure, suppose you are having a some workpiece like this, and it is under some hydrostatic pressure from all sided. Okay, the hydrostatic pressure workpiece like this metal sheet. Just a second. Okay, so there is some metal sheet, something like this, and which is under some hydrostatic pressure, or it has been kept under, you can say, in the sea water. Okay, so obviously this will be under some kind of, under some kind of pressure. Okay, so here you can see the forces or the stresses developed due to hydrostatic pressure would be sigma 1 will be equal to sigma 2 will be equal to sigma 3, and the value will be equal to 3. Okay, so take the case when you are applying hydrostatic pressure, the principal stresses will be sigma max. You can say sigma max will be equal to your minus p. Sigma minimum again will be equal to minus p. Okay, so now try to see sigma 1 minus sigma 3 equal to y equal to 2k. We are applying your Tresca yield criteria in the case of hydrostatic pressure. So put the values of sigma max minus p, sigma minimum minus p, minus plus. So this will be equal to 0. Okay, so since the value is 0, which is not equal to your yield criteria, that is 2k or y. Okay, so we can say that in the case of pure hydrostatic stress, the yielding will never happen. Okay, so wherever if you have any metal component or any workpiece which is under the action of, or which is kept in a pressurized fluid or chamber, it is not going to yield plastically. Okay, it will remain in the same position wherever it is. Okay, so hydrostatic pressure, wherever you feel when there is a any metal workpiece or any test specimen which is under the action of hydrostatic stresses, this is not going to yield, or it is not going to fail. Okay, one more example to elaborate, more with more clarity about the effect of hydrostatic pressure. Okay, so let us take the state of stress where sigma 1 equal to 80 megapascal, sigma 2 equal to 45, sigma 3 is equal to minus 30. So these are the given values for a material which is under loading, and suppose you want to give 50 megapascal of fluid pressure. Okay, so this ultimately this will be added in all the stresses sigma 1, sigma 2, and sigma 3. So let us try to understand the yielding without hydrostatic pressure, then we will try to understand with hydrostatic pressure. Okay, so in the beginning, sigma 1 is equal to 80, sigma 2 45, sigma 3 equal to minus 30 megapascal. Let us take this case. This is sigma 1 minus sigma 2, and okay, so even if it is not required, I have done like this. You can simply do like this. Okay, sigma max, what is the value of sigma max? Sigma max will be 80. Okay, sigma minimum, what will be value? Sigma minimum will be minus 30. Okay, so apply the yield criteria. Sigma max minus sigma 3. This would be 80 minus of 30. Okay, so this will become 110. Okay, so since you have applied your hydrostatic pressure, it will not give any impact. Okay, so I think it is already clear. Let me not elaborate more on this effect of hydrostatic pressure. Okay, because this is already, time is running fast, and I have to finish one more connected yield criteria. Okay, if there is any confusion on the hydrostatic pressure, then I will elaborate more. Any query? Otherwise, I will move to the next yield criteria. Okay, so I expect the effect of hydrostatic pressure on yielding does not give any impact. It is clear to all of you. Okay, so now let us take the another yield criteria, that is the von Mises yield criteria. So Mises yield criteria, the function is expressed in the terms of principal stresses like this, given by equation number 10, that is sigma 1 minus square of sigma 1 minus sigma 2 some plus sigma 2 square of sigma 2 minus sigma 3 plus square of sigma 1 plus sigma 3 is equal to C. So this is equal to a new constant. It is again not equal to your Tresca yield criteria. This constant is again different than your Tresca yield criteria. Okay, so to find the value of C in uniaxial tension test, the case may be handled. In this test, when sigma 1 is equal to yield strength value, the yielding will occur. Okay, so we are aware that in the case of uniaxial testing, your sigma 1, that is in the case of your uniaxial testing, your sigma 1 should be equal to your yield strength sigma y, and your sigma 2 and sigma 3, obviously these would be 0. Okay, so in the case of this is a typo error here. Sigma 1 minus, there is nothing. Okay, it has been by mistake it got remained. Okay, sigma 1 is equal to y in the case of uniaxial loading, and sigma 2 and sigma 3 is equal to 0. Put these values in equation number 10. Is sigma 1 equal to y, sigma 2 equal to 0, sigma 3 equal to 0. So this term will be 0, and this term will be this will be y minus 0. So y square, here again y minus 0 square. So this will be y square plus 0 plus y square is equal to constant. So in so now this one Mrs. equation yield, it comes 2y square equal to C. In the case of this was the case of uniaxial loading. In the case of pure shear case, what will be the value sigma max? We have already elaborated during the Tresca yield criteria. In the case of pure shearing, sigma max would be equal to sigma 1, sigma minimum will be equal to sigma 3. Okay, and this will be equal to negative of sigma 1, and the value of sigma 2 will be equal to 0. Put these values in your equation number 10. You will end up that sigma 1 is equal to sigma 1. So this will be your okay. So if you put these values, you will get this particular expression, that is 6k square is equal to C. Okay, put these values. K is again a constant. Okay, put these values. This will be sigma 1 minus 0, sigma, it means sigma 1 square. So this will be your sigma 2, it means 0 minus sigma 1. Okay, so this will be thrice of sigma 1 square. Okay, so since this will okay, yes, you can put this value in your equation 10, and you can compute sigma 1 minus sigma 2 square of sigma 1 minus sigma 2 plus minus sigma 3 plus square of sigma 1 minus sigma 3 equal to 6k square is equal to 2 pi square. Okay, so from this is in terms of your principal stresses. Okay, if you want to give the general form of your one misses yield criteria in terms of your stress components. So the stress component would be sigma x, sigma y, sigma z, tau xy, tau yz, and tau xz or zx. So you can write the general form of your one misses yield criteria. This will be given by your equation number 14. Let me not read this long equation. You can easily remember it. Okay. So be careful. The two equation, that is equation number 14 and 13. These both are the equivalent. Okay. Rearrange the one misses criteria and try to see equation number 30. So what will be the value of y? That is the value of yield stress. This will be equal to y equal to 1 upon root 2. We are simply taking we are simply calculating the value of phi from equation number 30. Okay, so this will end up with the value y equal to something like this expression, square root of this. So the amount of principal stresses in this equation is just at yield limit. If equation is analyzed, y should be replaced with sigma bar, okay, which indicates equivalent stress. So you can replace y with your equivalent stress, and this you may represent by sigma bar. Okay, so the equation for your equivalent stress would become sigma bar is equal to, again, same expression from the equation number 50. Okay. So this is about one misses yield criteria. Let us try to elaborate this using some examples. Okay. Let us take example of the same equibiaxial tension, that is axis 1, 2, and 3. Okay. Sigma 1 equal to sigma 2 is equal to sigma. This we are already aware. Sigma 3 is equal to 0. Substitute the value in the these values in the expression for equivalent stresses. Okay. So in the case of uniaxial loading, you are applying this one misses yield criteria. You are putting the values of sigma 1, sigma 2, sigma or sigma 3. So this sigma bar would yield sigma bar equal to 1 by root 2, sigma 1 minus sigma 2, sigma 2 minus sigma 3, sigma 3 minus sigma 1 minus sigma 3. Okay, square root of it. Okay, so this will be sigma. This will be 0. This will be sigma square. This will be again sigma square. Okay, so this expression will be equal to 1 by 2 twice of sigma square, power 1 by 2. Okay, so when you remove this power, this will become, your square will go, okay, and you have to put a square root here. Okay, this was already under square root. Okay, so you can cancel it. Okay, so in the case of your one misses yield criteria, when you are applying one misses yield criteria in the case of equibiaxial tension, this is yielding equal to y. Okay, so this is yielding equal to your yield stress. Okay, so this may be written as equal to pi. So this is why sigma bar is equal to your equivalent stress is equal to pi. So for the case of biaxial equibiaxial tension, the yielding will occur when your stress in each direction is equal to y. Okay, so you can see in the case of what was the result, the stress required in the case of Tresca yield criteria. In the case of Tresca yield criteria, you can see the stress required was again same value, sigma equal to y. So in the case of uniaxial in the case of uniaxial equibiaxial tension, you get the same value for both the criteria, whether it is the Tresca yield criteria or von Mises yield criteria. Let us take one more, because we try to see the effect of your hydrostatic pressure in the case of Tresca yield criteria. Now we will try to see the effect of your hydrostatic pressure in the case of von Mises yield criteria. Okay, so this we are aware in the case of hydrostatic pressure, your principal stresses would be sigma 1 equal to sigma 2 is equal to sigma 3 equal to minus P. Substitute these values in the expression, that is the equation number 16. Equivalent stress will be given by sigma bar equal to 1 by square root of 2. Solve it. It is coming equal to 0. Okay. So since 0, the net effect or the equivalent stress developed due to the hydrostatic pressure is equal to 0. So this will be always less than your yield strength, and it can be concluded that in the case of your von Mises yield criteria, the yielding will never occur due to the hydrostatic pressure, or the hydrostatic pressure does not affect the yield strength or the yield point of your test component or your metal. Okay, so this has also been yielded the same value in the case of one Tresca as well as in the case of von Mises yield criteria. Okay, so for today I will stop here.